Let's get started. So we've been talking about nuclear structure, and up until now we were talking about mainly odd A nuclei and relying on the idea that we could attribute the ground state spin imparity and the spin imparities of at least the first few low-lying excited states of those nuclei as being due to the single unpaired nucleon that existed in that. So we would say that if we have a nucleus that has one unpaired neutron, whatever spin imparity of the shell model orbital that neutron is in determines the spin imparity of the ground state of the nucleus. And then as we gradually promote that one neutron to the next available shell model orbitals, we predict the excited states. And we saw where that worked reasonably well and where there were shortcomings of it, and a little hint as to why there might be shortcomings having to do with the fact that, for one thing, nuclei are not necessarily all spherical. Now we're going to talk about slightly more complicated nuclei, namely even A nuclei. So these are nuclei where you have either an even number of protons and an even number of neutrons, or an odd number of protons and an odd number of neutrons. And again, both cases, the sum of the A's will be even. So let's start with the even nuclei for a moment. So remember, as you're filling up those shell model orbitals with the neutrons and protons, the neutrons go into respective shell model orbitals, and as you add them one at a time, they pair up in such a way so that if there's an even number of neutrons, the neutron spins all add up to 0. And if you think about it, suppose I have a shell model orbital which, for the sake of argument, let's say has spin 3 halves. Okay, so it's a p3 halves orbital, for example. How many z substates of that shell model orbital are there? How many neutrons can I put into that orbital? It's a 3 halves. J is 3 halves. 4. 2j plus 1. Okay. And that's because there are 4 separate z projections of that total angular momentum j. I could have plus 3 halves, plus 1 half, minus a half, or minus 3 halves with respect to some z-axis I define. Okay. As I go putting in those neutrons, the first one can go anywhere. Let's just say it goes into the plus 3 halves magnetic substate, or z projection. When I put that second one in, it will go into the minus 3 halves, so that those 2 neutrons add up to spin 0, so that the nucleus, which has 2 neutrons in that p3 halves orbital, still has total spin 0. Okay? And that'll happen every time I add pairs of neutrons. And the same thing will be for protons. And as a result, what I expect then for even nuclei, that is nuclei that have even numbers of neutrons and even numbers of protons, that the ground state spin imparity will always be 0 plus. And that's universally observed. There's no even nucleus for which that is not true. Okay? And it's because of this pairing interaction that likes to get the neutrons paired up with neutrons and the protons paired up with protons. Okay, so that's something you should know and understand why it's that way. Okay, odd nuclei. These are the most complicated nuclei there are. Okay? And there are very few stable ones. In fact, I think I mentioned the other day there are only 5 of them. But there are lots of odd nuclei that are radioactive. We would like to be able to understand their structure as well. So I've got an odd proton and an odd neutron. And so the ground state spin imparity of an odd nucleus is determined by the coupling between that odd proton and the odd neutron. And so I have to think about the angular momentum of both the neutron and the proton, and remember that these are vector quantities. Okay? They're not necessarily pointing in the same direction. So if I want to determine the spin imparity of that odd nucleus, I have to add these 2 angular momentum vectorially. And in general, there isn't a single possible outcome. So remember, if I have 2 vectors, j sub n, where this is the j of the neutron, that's the j of the proton, I can determine those from the shell model. That is, I go and look and see, what is the number of that neutron. Maybe it's the 51st neutron in this nucleus. I can go look at the shell model scheme and say, what would be the spin imparity attributable to that one neutron? And similarly for the proton, what is the proton number? What is the shell model orbital that would correspond to? So in principle, I should know what these 2 things are. What I don't know is how they're oriented relative to one another. Because these are distinct particles, they're not necessarily going to pair up like that. So if I want to determine J, I have to remember how to add angular momenta vectorially and quantum mechanically. And this is a problem I know a lot of folks are struggling with, but it's very important to go through this and try to understand how it works. So regardless of what angular momentum you're adding, whether it's intrinsic spin, orbital angular momentum, or J, the rules are the same. So if I have two angular momentum vectors, there's a range of possible outcomes, and you can think of that as being due to the range of possible relative orientations of those two vectors with respect to each other. And the quantum mechanically sort of weirdness about this is that in principle you would think those vectors can be arbitrarily oriented with respect to another, and so in fact you could get basically any answer you like. Quantum mechanics says it ain't true. They're quantized orientations, if you like. And what that means is the magnitude of the resulting vector, that is the length of that vector, has a range of possible values. The maximum value corresponds to the case where the two spins are pointed in the same direction. And so I would simply add together the magnitudes of these two vectors algebraically. But on the other hand, the extreme case for the minimum value is when they're oppositely oriented. And so then the minimum value is Jn minus Jp. And all integer steps in between are allowed. So for example, let's just go through a case. So suppose J sub n, let's take a simple case, is a half. And J sub p, let's say, is 7 halves. Just for example, okay? So what are the possible J nucleus I could get by adding Jp and Jn? Okay, according to this little nomenclature over here, what are the possible values for the magnitude of J nuclear? What's the maximum it could possibly be? 4. 7 halves plus 1 half. And what's the minimum it could be? 3, the difference between them. Okay, this is a simple case, and I chose it purposely because there are only two possible orientations of that J vector of a half. Okay? Let's do a slightly more complicated case. Suppose we make this 7 halves. Now what? What's the maximum? 7. What's the minimum? 0. And everything in between. Which one is going to be the ground state spin of the nucleus out of all those possibilities? You might think that the lowest spin would be, I mean, classically we tend to think that orbital angular momentum or angular momentum and energy go together, but it's not necessarily true. And it may not be that the 7 is the one either. It's very hard to predict, and there's no guaranteed rule that you can follow all the time and know you're going to get the right answer. So in general, if you have an odd-odd nucleus, you can only predict a range of spins and parities. There is an empirical rule that is most always obeyed, but not uniformly. And that is, remember the deuteron. The deuteron is the sort of simplest possible example of an odd-odd nucleus. It's 1 proton and 1 neutron. In that case, which way are the spins oriented in the ground state? Parallel, because the spin and parity of the deuteron is 1 plus. It turns out in most odd-odd nuclei, the ground state will have the total angular momentum, the spins of the nucleons, the intrinsic spins of the nucleons involved, parallel to each other, just like they are in the deuteron. Okay? So if I were guessing here, so let's go back a minute. This is let's say it's a 1f 7 halves orbital. What is the L value of that orbital? What does the F mean? I heard 3, I heard 4. It's 3, right? Remember, so this is just a name or a letter, and this is L. So S has L equals 0, P has L equals 1, D has L equals 2, F has L equals 3, G has L equals 4, et cetera, okay? So this guy has L equals 3, and what is the spin of the neutron? What is S? The intrinsic spin of the neutron. What kind of particle is a neutron? Boson, fermion? It's a fermion, which means it has intrinsic spin of 1/2. 1/2, right. Proton? Same thing, okay. So for this particular orbital that I picked, L equals 3 and the intrinsic spin is 1/2. And I said that the total J of that state is 7/2. So what does that tell you about the orientation of the L value and the spin for the neutron in that level? They're pointed in the same direction because 3 plus 1/2 makes 5/2. So they must be pointed in the same direction. And same here. Okay. So if I have this odd nucleus that happens to have J equals 7/2 neutron, J equals 7/2 proton, and I'm trying to predict the spin in parity of the ground state of that nucleus, I want to try to pick the case where the intrinsic spins of the neutron and proton are pointed in the same direction as they are in the deuteron. So that would correspond to the case where the total spins are pointed in the same direction here. Okay? Because let's say J of the neutron is, sorry, L of the neutron's this way, J of the neutron's that way, so the total spin's that way. Same for the proton. I want the neutron and proton spins to be parallel because that's what the deuteron likes to do. Therefore, I would predict on that empirical basis this would be the most likely ground state. Not always true, but if you had nothing else to go on, that's what you'd say. And the reason is it's like the deuteron. It's an odd proton and odd neutron, and the spin-spin part of the nuclear force likes to have those spins pointed in the same direction. Okay. Now, we've covered even nuclei in their ground states, odd nuclei in their ground states. But we know that nuclei are complicated objects. They don't just exist in their ground states. They have large numbers of excited states, and we'd like to try to understand why they have the structures that they do. So, for example, let's just pick, not exactly a random choice, but a typical sort of even nucleus. This is tin 130, okay? It's chosen because it's a relatively simple case. Remember, 50 is one of our magic numbers, so it's got a magic number of protons in it. What that means is that the protons close whatever shell model orbitals are available to them, and that's a very stable configuration which takes a lot of energy to alter. And so if I'm thinking about how would I make excited states of this nucleus, chances are it would cost me a lot of energy to disrupt any one of those protons out of those closed shell model orbitals. And therefore, it's more likely that what's going on to make the excited states is I'm doing something to those neutrons, because I don't have quite a closed shell of neutrons. What would be the magic number of neutrons that would be required to make that nucleus doubly magic? (82), exactly. 82 is the next magic number. So I'm 2 neutrons away from that. So if I go and experimentally study tin 130, what I find is, according to what we just said, no big surprise, the ground state has spin in parity 0 plus because it's an even nucleus. The first excited state is a 2 plus state. And in almost every even nucleus, that's the case. Regardless of where you are in the periodic table, there are very few exceptions that the first excited state is not 2 plus. Okay, so that's, first of all, something we try to understand. Why do even nuclei typically have 2 plus excited first states? And then above that, in this particular case, there's a range of different spins and parities in no particular order. Okay? Now, let's try to understand this in terms of what we've learned so far about the shell model. Suppose we try to explain the states we see here based on the shell model orbitals that are available to tin 130. Okay, so here's the shell model diagram again. And we're talking about tin 130. So we've got our closed proton shell. And my argument was that there's a big gap in energy between proton number 50 and the next available shell, that 2d5 halves. And these excited states we're talking about are relatively low energy. So I'm not going to move the protons around. But I'm 2 neutrons away from closing that 1h11 half shell and making 82. So maybe there's some room up there to play around with the neutrons and explain the excited states. Okay. So let's assume that's what's going on and see what spins and parities we would predict for those excited states. So in red here and blue is meant to be the shell model diagram near the top of the level scheme for the 80 neutrons that are in tin 130. So each one of the dots is a neutron, and to get up to my 80 neutrons in tin 130, I filled the 2d3 halves orbital with the 4 neutrons that are allowed to go there. I filled the 3s a half with the 2 neutrons that are allowed to go there. And although there could be up to 12 neutrons in the H11 halves, and remember, these numbers are just 2 times that plus 1. In tin 130, I've got 2 openings there. I've got 2 unfilled orbitals. So suppose what's going on in making these excited states is I take one of the neutrons, let's say from the 3s a half orbital, and I excite it into one of these previously unoccupied 1h11 half spaces. Okay? So what that would do then is it leave me an odd neutron in the 3s a half orbital and an odd neutron in the 1h11 halves orbital. Okay? I mean, that certainly should happen. The question is, what spin in parity would that then produce? Okay? So now I've got h11 halves, that's one odd neutron there, and s a half, and I add them together according to the rules we just had here. So I would expect to get 1 half plus 11 halves, or 6, or 1 half from 11 halves, 5, and they would have negative parity because, remember, the way you determine the parity of a state is to multiply the parities of the individual orbitals that are involved. This state has positive parity because L equals 0. This state has negative parity because H means orbital angular momentum of 5. Minus 1 to the 5 is negative. So if that were the case, that is, if I took a neutron, pushed it from this level up to here, I would expect to see states of spin 5 or 6 with negative parity. Okay? And just to go back for a minute, I don't see that. Well, here's a 5 minus. So maybe that state up there is one of those possible outcomes. It could be, but it's not the 2 plus. You can't get a 2 plus from doing what I just described. Okay, let me dig down a little further. Suppose instead I go down to the 3 halves orbital, which was full. I take one of those neutrons and again push it up to the first state that's energetically available to it, namely the H11 halves. So now, what do I have? I have an unpaired H11 halves neutron and an unpaired D3 halves neutron. And now I have to add these 2 angular momentum together vectorially and quantum mechanically. And so I play the same game we just did there. The maximum I can possibly get is by adding these 2 algebraically. 11 halves plus 3 halves is 14 halves, or 7. And I take the difference, 11 halves minus 3 halves, 8 halves, or 4. And again, it's going to be negative parity because this orbital has positive parity because L equals 2. This has negative parity because H means L equals 5. So I would predict a range of spins and parities for these states, 4 minus, 5 minus, 6 minus, 7 minus. Okay? And again, I go back, and well, so here's a 7 minus, here's a 4 minus. Maybe that's what's going on up there. But again, I don't get a 2 plus. Okay? And you can play around a lot with this, and you'll find it's very difficult in terms of a shell model scheme to figure out why this nucleus or all the other even nuclei have that 2 plus first excited state if this were the picture. And in fact, so just to summarize, almost all even nuclei have J pi equals 2 plus first excited states. The energy of that state decreases smoothly as you move up in A. And this is a figure that's in Lily's book. It's also in Crane's book. So this is the energy of the lowest 2 plus state in even Z, even N nuclei, so even nuclei. And what you see is more or less a smooth trend of decreasing energy as you go up in A. You notice that there are peaks, and these, not surprisingly, are associated with the neutron and proton magic numbers. But once you get away from those closed shells, it's a fairly smooth trend of decreasing energy as you move up in A. The other thing that you find is that there's some systematics in the energies of not just the first 2 plus level, but in many of these nuclei, the second level, the second excited state, is a 4 plus level. Or at least there's a 4 plus level not too far away from the 2 plus level. And what you find is that there are 2 kind of classes of nuclei that you can identify based on the ratio of the excitation energy of the first level that has spin and parity 4 plus to that of the first level that has spin and parity 2 plus. There are a bunch of nuclei that have a ratio of those 2 energies of about 2. Not exactly 2, but close to 2. And it turns out if you look in the if you look in the chart of the nuclides as to where they occur in A, it's these nuclei down here. So you can see there's a lot of scatter in that individual ratio of the 4 plus to the 2 plus, but here's that ratio equal 2. That's not a bad approximation to that, okay? So for nuclei below about A of 150, the ratio of that 4 plus to 2 plus for even nuclei is about 2. Then you notice that there's some funny business going on here as we get around neutron magic number 82. And then there's another class of nuclei. There's a bunch of nuclei in here between about mass 150 and 190 or so, and another group of nuclei up here around mass 230, 240, where that ratio is much, much higher. Again, this is the ratio of the first 4 plus energy to the first 2 plus. And this one is remarkably constant. And the value is 3.33, very nearly, okay? So this is telling us something interesting about nuclear structure. Namely, there are these big trends in the energies of these excited states, which cover the whole chart of the nuclei. And there are characteristic energies for these states which persist over large numbers of nuclei. And the suggestion then is that this is not a single particle phenomenon, that this is not something you can blame on a single neutron or proton. Okay, so this just says in numbers what I said in words a minute ago. So this is suggesting there's something collective going on, that it's not simply 1 or 2 neutrons or protons that are causing these excitations. It's something collective involving almost the entire nucleus. Okay? And it turns out the 2 kinds of collective excitations we've identified, and I'll show you the arguments for them in a minute, are vibrations and rotations. Okay? And what we're picturing now is a very different model for the nucleus. So in this context, we're not thinking of the individual neutrons and protons anymore. We're thinking of the nucleus as a charged liquid drop. Okay? So it's kind of like a liquid. It has an electric charge. We've already seen that the nuclear material is not compressible. It doesn't like to be compressed. So it's kind of like water in that regard. And so you can think of it as an incompressible fluid. And what are things you can do to a droplet of water? Well, one thing is you can make it vibrate. Okay? You can imagine banging on it with a hammer. Okay? Okay, a little hard to do in practice, but you get the idea. You bang on it with a hammer, and what's happening? It'll ring. It'll ring, okay? And it can ring at different frequencies. And that's kind of what nuclear vibrations are all about. And the other thing you can do is you can make that water droplet spin. Okay, that's rotation. And in classical terms, the vibrations and rotations would be basically continuous excitations. You could have any old amount of energy tied up in these things. But it turns out quantum mechanically, again, these excitations are quantized. And we're going to see that that explains those characteristic patterns of the excited states of the even nuclei. So let's start first with vibrations. And the idea here is that we're going to assume we've got this charged liquid, which is nuclear material. We're going to imagine it's a continuous liquid now. We're going to forget about the fact that there are discrete neutrons and protons in there. And we're going to assume the fluid is incompressible because, again, that nuclear force tends to be repulsive when we push things together too tightly. So it doesn't like to be compressed. And so what we're imagining here is you have a nucleus which in its ground state is a sphere, spherically symmetric, and we bang on it in some way. And the banging on it could be a nuclear reaction that we do, or it could be a radioactive decay that excites the nucleus out of its ground state to some higher lying level. What we're imagining then is the nucleus oscillates around this spherical ground state shape. So the nucleus is a sphere in its ground state, and it can elongate in one direction or elongate in another direction in such a way that the density doesn't change. Okay, that's what we mean by incompressible. So the volume of the nucleus does not get altered in this process. And the picture we have then is you can write down a radius for the nucleus that is time dependent. Okay, so I'm imagining that I'm sitting here at the center, I measure the distance to a surface of the nucleus, okay? And that surface point is moving in time because the thing is oscillating. So there's some average value which you could attribute to the ground state, and then there's some time dependence, and the way it's parameterized is in terms of these spherical harmonic functions we talked about before. Don't worry about this stuff. This is just to show you that it is understood how to do it, okay? But the point is you have some ground state radius, and then you have some oscillatory behavior superimposed on that. Okay? And if you think about what the shape of the nucleus could then look like, This is out of Lily's book, and he's showing you the lowest vibrational excitations of a spherical system. So we're imagining that the ground state is the dashed line here, okay? And what's called the monopole excitation, the lowest kind of excitation you can imagine, is the nucleus swells up and contracts. Swells up and contracts, okay? Now that violates something I said earlier, because if that were true, if it just gets larger, what happens to the density in going from this shape to that shape? It decreases. And similarly, if the nucleus compressed and the radius got smaller, the density would go up. Well, nuclear fluids don't like to do that. So this doesn't happen. Okay? Classically, this could happen. We don't see that experimentally, so that's not what's going on. This also doesn't happen. Okay? And the reason is a little bit different. If I imagine the ground state is the dashed sphere there, in this so-called dipole excitation, what's happened to the center of mass of that sphere? Is the center of mass of the solid sphere the same as the center of mass of the dashed one? No, they're displaced with respect to each other. So that corresponds to the nucleus as a whole moving, in this case, in the upward direction. That's not what we're talking about here either. We're talking about the nucleus sitting at the same location and just oscillating about that shape. Okay, so this isn't what's going on either. Okay? The lowest excitation that could be is this one. It's called the quadrupole excitation. And this is why we talked about this idea of quadrupole moments a while ago that you may not have cared for very much, but it's because it's important in trying to understand the collective excitations of these even nuclei. And so you can sort of see why this might be called a quadrupole if you think about the spherical shape being that dash curve, the dash circle, and in the quadrupole excitation, what I've done is I've shrunk the nucleus in the x direction, and I've elongated in the y direction here, and I've turned it from a circle into an ellipse. And you can kind of think of that as being, taking matter away from these areas, so you can think of that as a negative density and adding positive density in the y direction. That's what a quadrupole is, okay? So this is called the quadrupole excitation. It turns out that the angular momentum associated with that is 2 units, okay? And to derive that is beyond the scope of this class. I'm not going to do it. If you want to see it, you can look it up in the textbooks. But take it for faith, if you like, that the excitation angular momentum associated with that quadrupole excitation is 2 units, and it has a positive parity associated with it. There's another kind of excitation called an octupole, where the nucleus looks like a pear rather than a sphere or an ellipse. Okay? This kind of excitation has 3 units of angular momentum associated with it and negative parity. Not only is the angular momentum quantized, it turns out the energy is quantized. That is, I can't just have any old energy for these excitations. And the way we picture this in the nuclear game is the same as the solid state physicists do. Okay, so if you've taken a course in solid state physics, you know that the vibrations of a solid are also quantized. So if I have a salt crystal or something like that and I bang on it, the atoms or molecules in there vibrate in a very similar way to what we're talking about here, and those vibrations are quantized, and the units, the quanta of vibrational energy are called phonons. We typically think of them as sound waves in the classical sense, but quantum mechanically they're phonons. And the same thing is true here. So we imagine in these even nuclei that have excited states which are described by vibrational excitations is that we're adding quanta of phonons to the ground state. So the first vibration of a nucleus corresponds to one of these lambda equals 2, that is spin equal 2, quadrupole phonons. So I'm adding to a ground state spin in parity, which I know is 0 plus. I'm adding an angular momentum of parity, and 0 plus anything is that anything. So if I add a 2 plus state to it, that predicts the first excited state is going to be a 2 plus state. That would explain why at least some of these nuclei have 2 plus excited states, because I've added one vibrational quantum to the ground state. Let's keep going. So now I have the excited state, which is a 2 plus level, and I add another phonon to it. So I add another J equals 2 phonon to a state that already has spin in parity 2. So I have a 2 plus state plus a 2 plus state, and according to my arguments over there, I should have all possible values of spin in parity from 4 down to 0. That is from 2 plus 2 to 2 minus 2. So I would predict 4 plus, 3 plus, 2 plus, 1 plus, 0 plus. In fact, it turns out because of symmetry considerations, the 1 plus and 3 plus states aren't allowed. Again, don't worry about it. If you care, it's in Crane's book. What that means is the possible outcomes are the even spin states, 0 plus, 2 plus, 4 plus. And then the next vibrational excitation would be this so-called octopole phonon, where I add one phonon that has 3 units of angular momentum and negative parity, and that would predict a spin-in parity of that excited state of 3 minus. Okay? So what I would like you to understand and be able to use is the notion that if it's a vibrational excitation that's going on in the nucleus, I would expect to see a level scheme that looks something like this. Okay, remember, it only applies to even nuclei, so I know darn well the ground state spin-in parity is going to be 0 plus. All even nuclei, with a very few exceptions, have a first excited state that has 2 plus spin-in parity. Okay? And we're saying that is due to one vibrational phonon being present in that nucleus. The next 3 states are going to correspond to the case where I've got 2 vibrational phonons, and those can produce spin-in parities of 0, 2, and 4. The energies of these phonons are more or less quantized, so I would expect this energy to be roughly equal to the same as that energy. That is, the spacing between the 0 plus and 2 plus should be approximately equal to the spacing between the 2 plus and these 3 states. And these 3 states ought to be close together in energy because it really doesn't matter very much in terms of energy exactly which way the spins are pointing. So I would expect 0 plus ground state, 2 plus first excited state, what we often call a triplet, 3 states of 0, 2, 4 positive parity, not necessarily in that order. For various nuclear structure reasons, sometimes the 4 plus is lower than the 0 plus. But we'd expect there to be 3 states nearby each other and roughly at twice the energy of this one. And then somewhere not too far away, a 3 minus. Okay? And as I said, we would expect then, because the spacing between the 0 plus and 2 plus is about the same as the spacing between the 2 plus and that triplet, that the energy of this either 4 plus or 0 plus or 2 plus second excited state divided by the energy of the first excited state would be about 2. And remember, for most of those nuclei below A equals 150. The other thing that we expect is that the assumption I had in starting out the discussion of vibration was the nuclei are spherical. Okay? That is, they're not inherently deformed. They take on these deformations only as a result of the oscillation, the vibration. Okay? So what I would expect then is the quadrupole moments to be near 0. And it turns out you can also make an argument about what the magnetic moments should be, and they should be close to 1 in these units. Z over A is about a half, so 2 times that should be about 1. Okay? So let's go look at a bunch of different nuclei. The example Lily gives is cadmium-118. It's a good example of a vibrational nucleus. So cadmium has 48 protons, and A is 118, so it's an even nucleus. No big surprise, ground state spin-in parity 0 plus. First excited state is a 2 plus. Okay, again, consistent with almost all even nuclei. The excitation energy of that first 2 plus level is 0.488 MeV. Okay, not terribly high in energy. And then we go look at the next set of levels, and you can see that there are 3 states at around an MeV, a little bit more than that, 0 plus, 2 plus, 4 plus. Okay, that's exactly what we expect for those 2 quanta, the 2 vibrational quanta, to add together to give us possible spins of 0, 2, 4. We said that the energy of those states should be about twice as high as the energy of this. In this case, it's closer to 2.5 times, but not so far away. Okay? And cadmium-118 isn't the only example by any means. This is a chart taken out of one of the other books I look at. So here you can see, a dozen or so different nuclei scattered throughout the periodic table. So here's nickel-60, 0 plus ground state, first excited state of the 2 plus at 1.33 MeV, and then you can see 2 plus, 0 plus, 4 plus. So this isn't exactly what I said. It's not always 0, 2, 4. But nevertheless, the energies of those triplet states are about twice the energy of the first excited state. And you can see across the table, all the way up here to here's mercury 200, again, same kind of thing. So this is a general phenomenon of a lot of nuclei, normally between A equals 0 and A equals 150, but not restricted to that. And the characteristic is 0 plus ground state, 2 plus first excited state, a triplet of 0, 2, 4 plus, around twice the energy of the first 2 plus. Okay, and that we think of as being due to vibrations. Okay, any questions about that? Okay, so let's go on now and talk about the other kind of excitation, which has to do with rotations. And so we've explained this part of the picture so far. Now we're going to go on to try to explain this part, where that ratio of the first 4 plus energy to the first 2 plus energy is more like 3.33. Oh, and here's just some more evidence for the vibrational picture. Remember, we expected for spherical nuclei the quadrupole moment, which is a measure of how non-spherical the system is, to be 0. And you can see, this is the quadrupole moment, that for nuclei up to about mass 150, the quadrupole moments, while not necessarily exactly 0, are small. And then notice when we get up here above mass 150, all of a sudden the quadrupole moments get very, very large and negative. And then over here they get large and positive. Okay, that's a sign that you've got a nucleus which is not a sphere even in its ground state. Okay? And this is up here, these are the magnetic moments. And remember, we expected the magnetic moment for a spherical nucleus to be about 1 in these funny units, and it's close to being that. Okay, so rotations. So now I'm going back to my picture of this nucleus as a charged liquid drop. I can't compress it. And now I'm imagining that it isn't necessarily true that even in the ground state, the nucleus is a sphere. If it were a sphere, could I observe it rotating? That's the correct answer. Why not? Suppose it were a sphere. I mean, normally, in classical terms, if I have a sphere rotating, I think, sure, I can tell it's rotating. How do you tell a sphere is rotating? You pick a point and watch it. Exactly. You watch it go around. Okay? So, if I have a classically sized object, I put a drop of ink on it and I watch that drop of ink go around. But I'm talking about a nucleus now. I can't put a drop of ink on that nucleus and watch as it turns. Okay? So if it's spherically symmetric, it looks the same at all times. And the weird thing about quantum mechanics is if you can't observe it, it isn't quantum mechanically meaningful. Okay? If I can't measure it, it might as well not exist. So what that's saying is there is no meaning in a spherical nucleus rotating because I can't tell. On the other hand, if it's deformed, I can tell. Okay? Because it doesn't look the same in all orientations to me as it goes around. And I'll show you some pictures in a minute of what we think these deformed nuclei look like. So the idea of a rotation only applies to systems which are deformed. And from those pictures I showed you a minute ago of the quadrupole moments, there are regions of the periodic table where we know the nuclei are deformed, namely between mass 150 and 190 and greater than about 220. And the way we picture these is what are called ellipsoids of revolution. And I'll show you in a minute what we mean by that. And again, the idea is we start out with a spherical shape and we measure how far away from sphericity we are with an equation that looks like this. So now I have a nucleus and I draw a radius vector from the center. And what I say is, depending on which direction I'm pointing my radius vector, the distance to the surface is different because it's not spherically symmetric. So there's some average radius, and then again I measure the deviation from spherically symmetric in terms of these YLMs. And this quantity beta is what we call the deformation parameter. And again, in a second I'll show you the picture. And it's just a measure of how non-spherical the nucleus is. And again, don't worry about the formulas. The point is you can do these calculations quantitatively. We're just trying to give you a qualitative understanding here of what's going on. And the two general shapes that are observed experimentally for nuclei are shown here. They're called prolate spheroids and oblate spheroids. And the way you can imagine, these are three-dimensional objects now, of course, sitting on a two-dimensional projection here. You can think about generating each of these by starting out with an ellipse. So I take an ellipse, which I draw in 2 dimensions, and to get the prolate spheroid, I rotate it about the major axis. Okay, so remember, if I have a sphere, the radius is the same in all directions. If I have an ellipse, obviously the radius from the center going this way, up and down, is longer than going that way. So I talk about the major axis of an ellipse being the longer of the two axes and the minor axis being the shorter one. In this case, the major axis would be in the y direction, the minor axis would be in the x direction. So if I take that two-dimensional ellipse and I rotate it about the major axis, so I'm rotating it in this way, I generate that three-dimensional object called a prolate spheroid. And sometimes this is called a cigar. You can imagine elongating it even more so it really looks like a cigar, a big fat cigar. Just for definitions, this type of shape is said to have a beta, a deformation parameter, which is positive. Okay? And quantitatively, what was observed experimentally is that the magnitude of this quantity beta, that is how non-spherical it is about 0.3. So they're not terribly distorted in their ground states. That is, they're not too far away from being a sphere, but they're not exactly spherical either. The other shape you can get, so again, you start out with an ellipse, and now you rotate it around the minor axis instead. Okay? So remember, the minor axis is going this way. I start with my ellipse, and I rotate it like that. And I generate a shape then that looks like that. That's called an oblate spheroid. And although this is exaggerated, that's kind of what the Earth looks like. Okay, because remember, the Earth is flattened at the poles a little bit. So if you draw a radius vector from the center of the Earth to the North Pole, or a radius vector out to the equator, they're not the same. It's further to the equator than it is, because the Earth is an oblate spheroid, and we call that a beta value, which is negative. Now these two things you can imagine then rotating. Yes?
How do they measure shape?
We'll get to that. I'll show you that in just a minute. Okay? Very good question. There are a couple ways you can determine. One comes from the quadrupole moment, which you can actually measure from the ground states. But the way it's often done here is using gamma ray spectroscopy, and that's what I'm going to show you, by looking at the energies of the excited states. That tells you something about the nature of the shape of the nucleus, which is spinning. Now, if you think about it a minute, imagine I had a nucleus that looked like that, and I say it's spinning, okay? In which direction is it spinning in a meaningful way for me to be able to observe it? How would it have to be spinning? Yeah, end for end, right? If I imagine it just spinning around the major axis, so it's rotating like that, it's kind of like what I said before with the sphere. Every point on it looks the same. I can't tell that that's rotating. On the other hand, if it's spinning like this, sometimes I'm looking at the long end, sometimes I'm looking at the short side. I can see this football spinning around. Okay? So quantum mechanically, not only don't I have rotations for spherical nuclei, I only have certain directions of rotation which are meaningful, okay, perpendicular to that major symmetry axis. Okay, so let's think about it, and this gets to the question of how you decide what the shape is. We can attribute an energy to rotation classically. So classically, you have a solid object, it's rotating with a certain angular frequency, omega. You know that there's a kinetic energy associated with that. So I have a sphere or an ellipsoid or whatever rotating. The kinetic energy classically of that is a half I, where I is what's called the moment of inertia of that object, times the frequency squared. And again, this is all classical in blue. So the angular momentum of that rotation classically is just the moment of inertia times that frequency. And so I can rewrite the kinetic energy in terms of the angular momentum, all classically, as just L squared divided by 2 times the moment of inertia. And the moment of inertia is the mass of the object. Okay? So we can take this equation and rewrite it quantum mechanically, just remembering that the angular momentum is quantized as units of h bar. And there's this funny way of how I calculate squares quantum mechanically. So the energy now is h bar squared over 2I. That looks a lot like that. But then instead of L, I write I times I plus 1. Okay, where I is meant to represent the nuclear spin that's due to rotation. Okay, so I'm now going to use that formula to predict the excited state energies of a nucleus that's undergoing rotation. So my ground state, according to this formula, would have energy 0. So my ground state I'm measuring as my reference for all this. The first 2+ level, I would calculate, there will be a constant out front, h bar squared over 2I, which I don't know a priori, because I don't know how to calculate the inertia. I don't know the shape of the thing. But I'm assuming that this is a 2+ level. So I is 1 in that case, and I plus 1 is 3. So 2 times 3 is 6. So I would predict then that the energy of this first 2 plus level is going to be 6 units of this, 6 times h bar squared over 2I. When I go to the 4 plus level, the first 4 plus, again I use the same formula. The constant is the same because I'm assuming this thing is rotating like a solid. But the only difference is now I is 4 and I plus 1 is 5, so it's 20 times that. And so on for the 6 plus and 8 plus. So these numbers are just I times I plus 1 times this constant, which I don't know a priori. Okay? So what I would predict then, if you just go back a minute, the energy of that first 4 plus state divided by the energy of the first 2 plus state would just be 20 over 6. Okay? And lo and behold, that's 3.33, and that's what I observe for the nuclei between mass 150, 190, and then around 220. So that's very, very good agreement, just from this qualitative kind of picture. And it doesn't stop there. So this is, again, a figure out of Lilly. What he's showing you is the energy of, in this case, the first 4 plus level divided by the energy of the first 2 plus level as a function of the A of the nucleus. And the prediction we just made was that should be 3.33, and lo and behold, it is. And then he goes on to show you the other states. So the first 6 plus should be 7. It turns out to be very close to that. So it's not just the first excited state that looks like a rotation. It shows good agreement for lots of these excited states. You can see some deviations, and we'll see why that is in a bit. So it's not perfect, but it's a darn good approximation to what's going on for a lot of these nuclei. You can calculate, again, classically, what the moment of inertia should be if these things were really behaving as rigid bodies. So if I had a solid rigid nucleus that was rotating, I could calculate the moment of inertia in terms of that deformation parameter, beta, that I talked about. And this is a classical formula. It just comes out of classical mechanics, if you like, that the rigid body moment of inertia, if it's a sphere, it's 2/5 mr squared. And if it's a spheroid, meaning not quite spherical, it's 2/5 mr squared times 1 plus 0.31 beta, where beta is that deformation. From the observed deformations, we know that beta is around 0.3. So if you plug in the numbers for a typical nucleus, given its size, its mass, and that beta parameter, you would predict that this unknown quantity that gets multiplied by those 4s and 20s and 42s should be about 6 keV. I'll show you in a minute the experimental values are closer to 15 keV. And that suggests that these things may not be rotating exactly as a rigid body. Okay, so we can't quite get that h bar squared over 2I. The rest of the features seem to follow what you would expect from a rotation. So a very nice example of this is hafnium 180. And again, it's not the only case. There are literally hundreds of cases that look like this. So hafnium has 72 protons, and this isotope would have 108 neutrons. Ground state spin in parity is 0 plus. First excited state 2 plus. But notice how much lower in energy this is to what we were talking about a minute ago. When we were talking about the vibrational excitations, those energies were on the order of an MeV or so. Okay? And now we're talking about less than 100 keV. And this is more typical for rotations, that first excited state energy is quite low. The next one is a 4 plus. And notice the spacing is getting a lot bigger. The energy difference here is a lot smaller than the energy difference there. The one after that is a 6 plus, then an 8 plus. There's 10, 12, 14, 16. It goes up to about 60. And notice the spins go up in units of 2, h bar, and the spacing keeps getting further and further apart. That's typical of a rotation. And if we use the algebra we just wrote down a minute ago, we don't know how to calculate that moment of inertia properly, so we use the energy of the first excited state to tell us what it is. So we notice experimentally the first excited state has energy of 93 keV. I say that's due to 2 times 3 times h bar squared over 2I. Okay? I times I plus 1 times that quantity. And so I divide 93 by 6, and I get that quantity as 15.5 keV. And if I assume the nucleus faster and faster, I can then predict the excitation energy of the 4 plus level, the 6 plus level, the 8 plus level. And notice I don't do too badly. So I predict that the 4 plus level should be 310. It's actually 309. I predict this should be 651. It's actually 641, and so on. Good, not perfect. And the reason it's perfect is this thing isn't really moving like a rigid body. It is a liquid, after all. It's not really a solid. But very good approximation. Just real quickly, you might ask yourself, does this make any sense at all? I mean, I'm telling you, you can basically forget about the fact there are neutrons and protons running around inside these nuclei. We're talking about the whole nucleus vibrating or rotating. Does that make any sense? Well, one way to decide is the relative speeds of the internal motions of the neutrons and protons compared to the speed of either the vibration or the rotation. Okay? So if you think about it, and go back to what we said before about the neutrons and protons running around inside this nuclear potential or this nuclear well, the kinetic energy, if you can just use the uncertainty principle, is on the order of 20 MeV for an individual neutron or proton. That is, it can't be moving less than that. So the velocity of an individual neutron and proton in its shell model orbitals is on the order of 0.2 times the speed of light. They're whipping around fast in there. They're not just loafing around. So they're moving fast. The question is, how fast are these nuclear rotations? Okay? So you can calculate the rotational angular velocity. Again, classically, it's just the square root of 2 times the energy divided by the moment of inertia. We take the energy of the first excited state. We see that it's a 2 plus. We plug it into this formula. We can calculate that it's rotating at about 10 to the 20th radians a second. Okay, remember, there are 2 pi radians in a circle. So these things are rotating what seems to be awfully fast, on the order of 10 to the 20th times a second. Okay? But if you think about a single neutron or proton on the surface of that nucleus rotating around, you know the radius, you know the rotational speed. V over c due to the rotation is about 2,000ths the speed of light. So these rotations are actually very, very slow with respect to the intrinsic motions of the neutrons and protons. So the neutrons and protons run around like crazy. They hardly notice that the nucleus as a whole is rotating. So it actually does make sense to think of the nucleus slowly rotating as the neutrons and protons speed around inside it. Okay, so that just says what I just said. Experimentally, you're asking how you determine the shape. You look at the energies of these gamma rays which are emitted as these excited states decay back down to the ground state. So here are the excited states, the 2 plus, 4 plus, 6 plus. We'll see later on that the gamma rays like to carry away 2 units of angular momentum as the decays happen. So we step from the 8 plus to the 6 plus, then from the 6 plus to the 4, 4 to 2, 2 to 0. If you calculate those differences in energies, the difference between the 8 plus and 6 plus, between the 6 plus and 4 plus, and so on, you get those things I labeled E4, E3, E2. And remember, we're blaming all these on rotations, so we know how to calculate those excited state energies. If you end up taking the differences in those energies, what you predict is you get gamma ray energies that are equally spaced from one another. Okay? You get what's called a picket fence. What you expect to see are gamma rays that are all equidistant from each other. And this is real experimental data which illustrates that. And since there's a class standing outside and this is long already, let's stop here and we'll pick up here on Friday. Okay? But that's what's called a super-deformed nucleus. This is a nucleus which has a major axis twice as long as its minor axis, and it's spinning like crazy. Okay, see you Friday.